So after we have discussed how wave-like solutions appear and the wave-like asymptotes appear for the area function, let us discuss the technique, so-called quasi-classical or WKB approximation, for analysis of general Schrödinger equations of potential type and leading to similar solutions. So recall the Schrödinger equation with m equal 1 for simplicity has the following form. And in general, this is a rather complicated equation, but due to some physical intuition or from both classical or quantum physics, we understand that the solutions should be basically wave-like. And for example, when u of x is constant, then the solutions are, of course, just sine, cosine, or decaying or growing exponents. So this is a very simple mathematical fact. And let us try to understand how this kind of intuition can be generalized for the case when u is position dependent. And most interesting approach to this is to keep this Planck constant here, which in a certain sense will be assumed to be small explicitly, and analyze this equation, so to say, by perturbation theory in this Planck constant. But notice that this perturbation theory should be highly non-trivial, because if we just throw away this term, then this equation becomes not differential one, but instead algebraic, or which gives effectively says that psi can be non-vanishing only at certain points of x, which are compatible with energy of the particle. So we see that the case of h vanishing h bar is kind of very singular. So the proper way for asymptotic analysis of this equation is to search for the solution for the wave function psi in the following form. So instead of psi as a function of x, we introduce sigma as a function of x, and this factor in the exponent, please note that it has h bar in the denominator. This h bar in the denominator is the main reason for weirdness of this small h limit. But anyway, for the moment, we just say let psi be exactly determined by this equation, and use it as an exact transformation and substitute it to the Schrödinger equation, obtaining a certain equation for sigma of x. So in order to do this, we need, of course, to calculate the second derivative of psi, and this is just so one differentiation is simple, another again is also not very complicated. So here we differentiate exponent first, and then the first term in the brackets. Now substituting this second derivative into the Schrödinger equation, we obtain the following. Note that we just have trivially cancelled the exponential factor through all of the equation. So now it's convenient to slightly rearrange this equation, and so that it becomes sigma prime squared over 2 minus I h bar over 2 sigma double prime. And this equation is to a certain extent more convenient for perturbative study in h bar, because now we have some terms with derivative which do not disappear completely when h bar vanishes, as it used to be in the Schrödinger equation. So let us solve this equation order by order in small parameter h bar, which will exactly give us so-called quasi-classical approximation. So if we take h bar to the zeros order, then the equation is very simple. So this sigma prime equals to plus or minus square root of, and it is very useful to realize that this is just classical momentum, which can be obtained from the energy conservation. So it's quite straightforward to solve this equation. So it is quite straightforward to solve this equation, and actually the solution is sigma equals to integral of p d x prime to x. And the lower limit of integration is of course not important here. And so if we determine this sigma to the first non-vanishing order in h bar, then, so to say, first approximation for the wave function is psi approximately equal to exponent of I of h bar plus or minus integral of p d x prime x. And we see that due to two choices of the sign of the momenta in this equation, we actually have two linearly independent solutions, which correspond to particles which propagate to the right to the left in the region where momentum is real, and to decaying and growing solutions in the region where momentum is complex. Recall that this is very similar for what we have in the case of the area function, because for the area function we have two regions of the coordinate. In one of the regions the allowed momentum is real and the area function oscillates. In another region, in the prohibited region, the momentum is complex and the wave function decays. So this is, so to say, the simplest part of the approximation. It's a bit more technical, but still relatively straightforward to solve this solution to the first order in h bar. And this is deferred to your homework, but most importantly, it leads to the following factor in the wave function. After you search for the correction to the main solution, you will find that actually what happens is the additional square root of p of momenta appears in front of the first zero order approximation. And this is already a very legitimate approximation. And this square root of momenta in the prefactor in front of the exponent is especially convenient to be understood in the classically allowed region, where it means nothing but a conservation of the particle current on the language of the quantum mechanics. But what is most important for us is that, first of all, say intermediate conclusions, is that first of all we have a certain approximation for the wave function, and it is valid. It could be potentially valid almost everywhere, but we need to understand what are the limits of which determine its applicability. And of course, most importantly, we can understand these limits from the form of the solution itself. And by the form of the solution, we see that essentially this is a wave function which is locally a wave, and the length of this wave is constantly adjusted to the varying classical momenta. And of course, this wave-like approximation is valid as long as the wavelength of this wave doesn't change much on characteristic scales of the problem. So, in terms of strict criteria, this d lambda over dx should be much smaller than 1, and lambda is inversely proportional to the momenta of the particle. This criteria can be well defined, well derived formally, but for this you can search for the textbooks. But it has very simple and straightforward interpretation that a wavelength should not vary much on the scale of the wave itself. Otherwise, this locally wave-like approximation is not very well defined. And of course, this approximation can easily break down, and it's very straightforward that, to see that it breaks down in certain special points, which are called turning points, in which the momenta vanishes. And these points will play a very important role in our consideration. And before we conclude this kind of formal introduction to the quasi-classical approximation, let us recall what was the importance of the turning points in the theory of the area equation. And recall that in the area equation, in the standard area equation, the turning point is at x equal to 0. And from this discussion, we understand that far from the turning point at both sides, the quasi-classical approximation should be valid. So this solution is a legitimate one. And of course, since in the immediate vicinity of the turning point, this approximation is not valid, then the solution which is on the one side is linear combination of two exponents, because the solution is real, then on the other side it's only a single solution which corresponds to the decaying exponent. And this means that the turning point at which the quasi-classical approximation breaks down is at the same time a point in the vicinity of which the solution with, contains two quasi-classical exponents turns to a solution which has only one quasi-classical exponent. And this is exactly a manifestation of the Stokes phenomena, which we are going to discuss in the next lecture.